Okay, so I want to start off thanking organizer inviting to here, and only know I need to give a talk actually 7 days ago. So the reason is because I'm a heavy ion physicist, and there's not so many heavy ion people here. So I actually what I'm going to talk about is complementary to what Ivan has been talking. He focused on the hard probes, IPT. I'm going to just focus on the low PT multi-particle production correlations. So there are actually just 3 parts. So I'm going to first define collectivity using multi-particle correlation in AA collision because the physics picture there is very simple. And then I'm going to make a connection to what is the nature of the multi-particle correlations and implication to collectivity in small systems. Okay, I'm going to then comment on some future opportunities. I also want to ask a question which I don't have an answer to, which is, can we learn something about the initial state from final state interactions? In other words, going from heavy ion collisions or PP hadronic scattering, we can measure many things. All right? Do we actually, we typically use the initial state as input, but the question is, can we go the other way? Okay, so I don't have any answer, but something that you may have some good ideas. In heavy ion collisions, right? So this is what we see in the detector. We see tens of thousands of particles in the central collisions, right? So it's after 10 to the minus 8 seconds. This is shown in the detector. And what we want to learn is actually space-time dynamics of the QCD evolution, okay? Which happens in 10 to the minus 22 seconds, which is about 10 Fermi over C. So we want to go from this image to this image. Obviously, it involves modeling. So since we see so many particles, the tool we use actually is multi-particle correlations for the software sector. So I can just split this space-time evolution into 2 parts. One is the final state stuff, right? Interactions, which happens in the T Fermi over C. Then this initial state part. The final state, the space-time dynamics in the low PD region actually is successfully described by hydrodynamics. Right? So we can actually model this quite precisely, compare very well with the data. But the initial state, there's large uncertainty in the heavy ion collisions because this has become precise, and this actually uncertainty here is become very important. So DIS obviously is one way to actually help to improve this situation, including constraining on the saturation or low X physics. So the DIS give us something about this one-body weakener function, or maybe correlations, also between parton-parton correlations in the initial state using different processes. But in heavy ion collision, what happens is different, right? So you have some initial state, multi-parton system, and the collision itself involves all the partons in the system, many partons simultaneously collide with each other. They are color connected everywhere, right? So we have this frozen PDF fluctuation, which is like a DIS, but it can fluctuate differently between the projectile and target, and then they collide. They liberate many particles in the different sources, right? You have this source, this drain is the source for particle production in a very small space. But huge energy are deposited here. They will rescatter and it drives the hydrodynamic flow. This is a longitudinal view and this is a transverse view of this picture. So in order to model this precisely, what we need, of course, is a 3-dimensional space momentum distribution of all the initial state partonic structure, right? So there's some of the flow actually can come from initial state, especially in the small system.
Is there a formal definition of such a many-body being a function?
Well, if you assume,
in this case,
I'm just saying, if you assume factorization, everything, you have a single body regular function, then you can just convolute them. But the question, of course, there's a conservation law, right? I don't think, I don't know. I mean, you have many body system in some initial quantum state, that's the wave function. Mathematically, you may be able to write down something, but you need a probe to measure those, right? So I think for Hebbian collation, if you think about how you model particle production, you have some initial source. Of course, many people use a classical picture for that, but in principle, you should start with some initial quantum state, involve many like a Fock state, right? So then model the particle production. But I don't know. I don't think there's any, even in PCL, any models, they don't do this precisely, right? They all has this high scale, low PD scale, where the low PD is just a phenomenology. There's no first principle.
I was just wondering if you want to work with an object which involves basically all the particles, we could right away go with a wave function.
Yeah. We need to go beyond PDF, right? So then what? I don't know. I'm not serious.
Yeah. Okay.
Yeah. Okay, so let me just define collectivity in Hebbian collation, because this is very clear. We produce many particles, right? There's some initial condition, which means there's a space momentum correlation, because I have some spatial deformation, some spatial shape, driven by pressure converted into a particle distribution in the final state in the momentum space, right? So, and this translation is taking place using modeled by hydrodynamics. We call hydrodynamic response to this initial state. And you can see this final state event by event. You don't need to average many events. You see event by event, there's a large modulation of the particle distribution in the azimuthal direction. Event by event, in the same centrality, looks very different from one event to next event. And we use this Fourier decomposition just to parameterize these different harmonics, right? So Vn, and you can go from one to a large number. So of course, only the first few modes are, visible, right? So you have a amplitude and the phase. In other words, it's a vector, which direction is pointing to. The flow direction is given by the azimuthal angle. So what do we know already, right? So we know there's a large event by event initial state fluctuation, which drives, this final state, the particle distribution. So each event, because you start from a different initial state, it follows its own hydrodynamic space-time evolution. And we need to have a small viscosity in order to for the efficient transfer of this initial state feature to the final state. So this is quite important. So this is a very qualitative statement here. So how do we quantify this reach? What do we see in the PP collation? People say there's a long range correlation. And actually, you see this very clearly in Hebbian collations. You have a two particle correlation in the relative angle, azimuthal angle, and relative pseudo rapidity. What you see is that for particle that's separated by 5 units in pseudo rapidity, 5 units, one particle goes to 10 degrees forward, another particle goes 170 degrees backwards. They know each other in the azimuthal direction. They are strongly correlated in the transverse plane because they see the same initial geometry. If you assume Booth invariant picture. So what people do is to get rid of the short range jet fragmentation contribution and just look the large directed ether region. You see this harmonic modulation averaged over many events, of course, in this case. And you can just extract this harmonic coefficient. This is the event average quantity. And this reflects, each component reflects different shape component in the initial state. This is obviously its interpretation. Now, In the high energy community, in PP collisions, people, starting from Tevatron error or, Rick field, right? So they actually try to study the underlying event because this is a very important background for the jet or hard probe process. What they typically do is they have a leading hard tag, and they look the underlying event relative to that to divide this into 4 quadrants, towards, away, and transverse, 2 transverse quadrants. They look the underlying event activities, right? In these 4 areas. And the other quantity, these things very important to understand this MPI, multi-party interaction, is to detect the difference between these transverse, 2 transverse areas. For example, plot this the difference as function of the energy of the probe, and they claim this is the term of the centrality. In PP collision, you also have a concept of centrality. What we are doing here is, I would say, is more general approach, right? So we just simply fully decompose this underlying event. We are looking what is based on the single particle picture, what is the corresponding 2 particle as Mosul structure. For pairs, they are separate in pseudo-rapidity. Okay, and it's actually more general than that because later on we can do multi-particle correlations. So this is the definition of collectivity. What is also quite unique in heavy-ion collision is that we see this fluctuation event by event, right? In DIS, we really, I don't think, we talk a Wigner function. This is the event average quantity. You have to accumulate a lot of events. But since each event in heavy-ion collision, you produce so many particles, we can actually study the nature of the event-to-event fluctuation. You see these 3 events in the central collisions. It looks different, right? So this Vn, the Phi can fluctuate event to event. That means we can, in general, study an object. It's a probability distribution of all the Vn's, all the Phi's, because the fluctuation could be correlated, right? Between the different Vn's or between different Phi's. This is the general object people studied for 10 years. There's a lot of measurement on this, but I'm not going to discuss any of those, right? So the way you access this observer is to think about, write this, this is a vector in the azimuthal direction, so you can just write in this complex form, right? So there's a Vn, there's a Phi, this is the, we call flow vector, and you do multi-particle correlations. You just see, this example is n particle correlations. You just insert different harmonic orders on the particles. And what the object, just ignore this detail, but the end object is basically these vector products of, you have m particles, so you have these m vectors. And in general, you just write down like this, right? So this is the amplitude, the phase, how they are correlated. And this is the moments of this probability distribution. In general, you get to fully decomposition of what I write in the previous slides. You get many, many such objects, which you can study very precisely, okay? And some examples you can understand very easily is the 2-particle correlation, which simply is the second moments of the Vn's. 4-particle give you this fourth moment of Vn. You can do a mixed harmonic correlations, correlation between Vn squared and Vn squared, or you can also insert a phase like this. So this average here is average over many, many events. So you, in other words, you try to access the probability distribution of a particular harmonics or joint probability distribution between 2 harmonics, okay? So the tool people use in statistics is to actually to measure this cumulance. They use cumulant, which is a combination of the moments to quantify the shape of this event-by-event fluctuation. So I'm not going to discuss any detail, but you understand what is variance, skewness, and kurtosis, right? So for Gaussian distribution, in other words, most simple fluctuation, just a random fluctuation, is a Gaussian. For Gaussian, fourth order cumulant equal to 0, right? So because it's Gaussian, in this definition, it basically is 0. But any deviation from that then tell you the non-Gaussian nature coming from either the initial state or final state, which is important. So all we need to do is substitute this x with the flow vector. What we derive that can be easily measured for 4 particles is this 4 particle cumulus, right? So it's a first moment, second moment is this combination, which tells you something about event by event fluctuation of a single harmonics. Let's say V2 event by event fluctuation, or maybe correlated fluctuation between 2 different harmonics. There are many other, I just give you 2 most simple examples. Many things has been measured. Okay, so just saying, looking at this, you already know if the Vn is the same for all the events, it doesn't fluctuate, you should get a negative contribution, right? This just become a minus Vn4. Okay? So you expect a negative value. Okay, so now let's then go to small system. Obviously, the normal particle you produce is much smaller. You do not have an intuitive picture just by looking at the event display. You do not see this event by event fluctuation. But statistically, you can still access those based on the quantity I defined earlier. So here, obviously, in these collisions, the size of the overlap region, even the highest multiplicity, is become much smaller. But it's still really hard for me to really, picture the fact that in a single proton collision, in the integrated over the entire phase space, you can produce 600 particles. All these particles do not belong to a few jets, okay? It's not belonging just like 3, 4 jets. It belongs to many, many mini jets. You can liberate many degrees of freedom through these multi-parton interactions in a single PP collision. This must tell you something about the proton structure fluctuation, right? I mean, tell you what kind of wave function, Fock state it can occupy, right? So I think the hadronic scattering, in principle, if you measure all the final state particles for many, many events, if you have the theoretical tool that you trust, you can, in principle, go back to get something about the initial state, which is beyond BIS, I think, right? But I don't know how to do it. So the hope is then going from the large system to a small system. You're changing the size of the system. You're changing the shape. You can vary the beam energies, right? You go from RIC to LHC energies. This hopefully you can actually increase or decrease the space-time dynamics. You're getting closer and closer to the initial state, okay? So going really good, doing this system size scan also allow you to really focus more and more on the initial state in using these multi-particle software correlations. So you can see the reach, this long-range structure in the all 3 systems. So this peak should be flipped, put it here. So this axis has been flipped, okay? But they all look similar, other than this short-range peak looks very different. This away-side peak is coming from dijet, so that's why it swings around, but you can see this long-range range, okay? So right now, the key question people were asking for proton-proton collision especially is where this long-range correlation come from. Does it come from directly from initial state momentum correlations? For example, KMD have a initial momentum correlations, right? I mean, so there could be initial state momentum correlation just from the structure function or CGC physics. Or if this momentum correlation is a final state response to a spatial fluctuation that do not have any momentum anisotropy. In other words, does this only coming from the hydro transport? So the key thing to resolve this, why we go to a different system, is to change the time scale, to really test the time scale for the emergence of this collectivity. They all look collective, but where it's come from? So the examples, I just give you examples of the interpretation. There could be many. For example, initial state model, for example, based on this saturation CDC picture, is the following. You have this extended object, take a high multiplicity PP collision. You have this color charge fluctuation which stretch in the rapidity direction. These are the sources of the particle production, right? And each of them are particle, when they are produced, they already have some momentum anisotropy, but they do not know each other. Then in other words, when you have many sources, even though each source have a momentum anisotropy, they tend to get diluted, right? So there's 1 over square root of n dilution. So in other words, in this picture, naively you expect when you go to large multiplicity, your anisotropy decrease. Okay. So, but in hydrodynamics picture, the larger multiplicity, the better you can convert the initial shape fluctuation into the momentum anisotropy. It's the opposite trend. Okay. So this picture really is you can start with this archiglossum initial condition, then simply put in hydro response. You can also generate additional momentum anisotropy. So the CGC and the saturation, obviously, this is well motivated, but it's really very hard numerically and theoretically to calculate. Okay, the modeling part is difficult. In the hydrodynamics, on the other hand, it's very straightforward. You can have a first order, second order viscous hydro equations. The only question will be whether the hydro is applicable, because hydro is for the long wavelengths. Approximation is the system must be in local thermal equilibrium. That condition may not be satisfied, right? So, so let's just show you what we see in the small systems. I have this PP collision, P-light and light, but this is low multiplicity region. So in other words, in the light collision, you can also have a small system event that produces not so many particles. As function of multiplicity, what you see is that if I just look the second moments, which is the largest one, V2, I see they are different, right? So the light is higher, P-light is higher, actually increase with N chart, because there's some geometry, right, which you don't have in PP. But nevertheless, you have large anisotropy in all systems, right? So in fact, these V2 harmonics, exist even in very low N charge, like mean bias. Typical minimum bias PP collision have a momentum anisotropy. I will show you later, this momentum anisotropy is actually multi-particle. It's not only between two particles. It's multi-particle long-range correlations. So do they have a similar origins? I mean, the feature looks similar, but maybe the origin are different. So the other smoking gun observation in the small system, here we use proton lab, which is still quite a small system, is that we see the V2 show a mass ordering. So in other words, particles with different mass have a different anisotropy. In the hydro picture, what you think about is that if I have a particle hadrons in the common in the fluid moving with some velocity, then there will be energy gain because of the motion, but this gain depends on is proportional to the mass, right? So the more massive particle gains more in momentum. So then what you do is that you divide by the V2 by the number of constituent quarks, the meson divided by 2, baryon by 3. The way we think about it is that in Hadron collisions, we think these mesons and baryons are produced in the hadronization, which means during the hadronization, you already have built up all the flow. You just coalescence, you add up the V2, okay? So in this case, once you apply this stealing, you see the mass dependence basically disappeared, and so all the particles collapse on top of each other. This is what we observe in AA collision, but this seems to also be observed in P-light collisions. So maybe we argue collectivity occurs in partonic level, but the CGC is also partonics, right? So the question will be, what is the origin for that? So let me just point out, since we know the flow, this anisotropy particle distribution have very strong event by event fluctuation. It's totally reasonable to think these harmonics, this particle azimuthal distribution should have a strong event by event fluctuation in PP or PA collisions. It's just natural to think about it, right? So in fact, there's an indirect evidence of the, Bjorn Schinker did some calculation where they use this diffractive EP, this error, JSI cross-section, they have to separate the coherent and incoherent cross-sections to show you that the proton substructure play a role, and this substructure will seed naturally through final state scattering different harmonics event by event. Okay, so let me just focus on one of the aspects, which is I think is quite interesting. It is so-called multi-particle nature of the ridge. So if you have some initial geometry, and then you go through a very strongly coupled evolution, then all the particles knows about each other. Okay, it's a collective. That means this collectivity must correlate between all the particles in the system. So it's not only the long range, but should be multi-particle. Okay, this is very different from the jet or dijet correlation, because this, you can think this is also collective, but they are collective only in the narrow phase space. Let's say inside the jet cone, right? They are collective in that way, but it's not due to final state effect. So one thing that you could suppress this, because in this case they are only appearing in eta1 and eta2. So if you require correlation between more than 2 eta ranges, you can suppress the dijet contribution, including this dijet contribution from this gluon linearized proton PMD picture, which was discussed earlier. You could have dijet correlation, right? Cosine 2phi like, but it's only between the 2 jets. So you can easily check this, whether this is the whether if you have multi-particle correlation in DIS, whether it's involving the full more than simple dijet. You can easily test it. So the way, as I said, so if you have a correlating between 3, for example, pseudo rapidities, this dijet will not contribute because it does not correlate between more than 2 pseudo rapidity ranges. In fact, you can just run PCA simulation, right? Anybody can run it. You calculate this 4-particle cumulant, which I said is related to the flow fluctuation. You can easily see in the standard method where you do not impose any rapidity separation, there's a large, jet contribution, but this jet contribution can be totally suppressed when you go to 3 sub-event, because this dijet doesn't correlate between 3 rapidities, you get a 0 signal, okay? And what do you see in the data? In the data, this is in P-light collation, you do see this negative contribution, which suggestive there's a 4-particle correlation, okay? And collective correlation. It's not due to jets, because you see standard method, 2 sub-event, 3 sub-event, only show a difference in the low multiplicity region. This is due to the dijet component. You can easily suppress that going to 3 sub-event. You still get negative signal here. And this line here corresponding to 4% of V2, okay? 4% is this big, this is bigger than 4%. But once you go to the PP, dijet contribution becomes so much bigger that even in the highest multiplicity, you need to really, you need to go beyond 2-particle correlation to show that you see collectivity, right? You need to look at the particles that are in 3 different rapidity ranges, they know about each other, at least, yeah. Right, so you can see these 3 sub-event methods still give you quite a large signal compared to 4%. So what the initial state model tells you? Well, in the CGC picture in this earlier paper, they argue that, okay, so I could in principle have a negative component here coming from this nonlinear, non-Gaussian, non-perturbative component of the gluon distribution function, right? This is the A to the 4th power negative. But then all the perturbative component, which initially they argue is important for this multi-particle production, is perturbative, actually does not give you negative contribution. But it turns out, since I already showed this is mostly due to dijet, right? This Glassman diagram actually is a multi-rapidity correlation. And it shouldn't be suppressed. But if I see my result, you can be surprised by going to 3 sub-event, and since this is not the actual contribution. So let me just give you a simple interpretation. If we measure a 2-particle long-range signal and also 4-particle signal, what do we know about this event-by-event flow fluctuation? Okay, so as I said, we see a non-zero 2-particle correlation, a non-zero 4-particle correlation, down to this is event with 50 particles in PP, and let's say 20 particles in Pli. Okay, so what this, and it's roughly independent of the multiplicity. If this is non-zero 4-particle moments, this is the kurtosis of the event-by-event fluctuation. This means there's a very strong event-by-event fluctuation, and it's not Gaussian. Okay, so what's the nature of the ridge? This multiple particle correlation, non-Gaussian nature of that fluctuation come from? Okay, I think it's challenging both initial and the final state model. So let me just then also point out that if you have an initial momentum anisotropy, but no final state rescheduling effect, okay, it predicts very different PT dependence or this multiplicity dependence of the collectivity. First of all, what you see is that it sort of give you this the data, and in the low PD region seems to roughly describe it, right? But whether you use a wrong proton means there's no fluctuation, or you use an eccentric proton by considering the subnucleons substructure of the proton, it doesn't matter. Okay, this is very different from hydro. Hydro should really depend on the shape, right? But the CGC, if you have initial state momentum correlation, it doesn't care. But in that scenario, then if you go from a small system to large system, as you increase the number of domains, color domains, it simply should be diluted, right? You have the more sources you have momentum anisotropy, but they don't know each other. Therefore, going from P-lat to lat, you should have a strong suppression. Okay, so this is something that one can try to test between the initial and final state. So the way you should see it is that you could have a situation, since both models seem to be conceptually problematic in the small system, you could imagine you have some initial state contribution plus some final state contribution. Initial contribution will die down as you increase the size. The final state will increase. And these two does not know about each other, right? Therefore, you have this random correlation. There should be a sweet spot where you can reach a minimum and then increase towards both sides. In fact, in this model calculation by Björn Schenker, where he has apicalosma, or CGC initial condition, and hydro calculation, you do see this structure. He has a better figure, which I can show, but I can show here. Okay, so let me just skip this part and also point out one interesting observation, which is very puzzling to me. I think this need to be checked in PP collation, because I think this may have some consequence to the DIS, because the DIS you do have final state interactions. Okay, so how big is these final state interactions? In the proton-led collation, in the high multiplicity events, which is about the top 0.01% of the events, you do see not only the light quarks have anisotropy, but even the D meson and J psi, they have non-zero momentum anisotropy. They are so heavy, right? They are heavy. Why they can develop anisotropy is not small. And on the other hand, you also see that if you look at the high PP particle, this is really high PP particle, right? 9 GeV and 12 GeV. Correlating with the soft particles, you see a near side ridge. And this open symbol is what you see in PP-like collisions, right? In PP-like collisions, you have this digest. But since you impose a pseudo-rapidity gap, the near side jet is not there, so you only see the away side particle from the away side jet. So there's a big peak here. But in the high multiplicity P-lat, you do see a long-range near-side correlation, even at a very high PP. Right? This implies there must be some final state interactions. I don't know, so people are still trying to debate whether this is a jet interaction or not. it potentially can be important if you have, so, you know, even if you have a large energy loss, strong interaction, you may have this long-range correlation. Okay, so I want to then go to extend what we are discussing here a little bit. What is the minimum requirement to see this long-range correlation? Well, we can start with a single color string, right? So in the PP collision is all straight picture. You have this boost environment. The particle produced from a string, which is boost environment. It has some length, but basically the particle produced from this string. So if you only have one single string, there's no final state interaction. You do not see near side ridge or pretty weak interactions. But you put as soon as you put the two strings not far from each other, they decay into particles. They will scatter with each other. Immediately, you will see a long-range correlation. Okay, this is an AMPT, which is a particle transport model starting from a PCA-like condition. Okay, so this is simulating E plus E minus to QQ bar with one single string. Then this one, you just split this 1981 TeV into two strings and put them close to each other, 25 Fermi. Okay, immediately you see the interaction produced on anisotropy. But however, once you go to Harrer, this is the EP collation or E plus minus collation in the lab, the data shows you that you select events with large multiplicity in the final state. Unfortunately, people claim, okay, I don't see large and V2. But however, this is because the statistics is really poor. If I put the 6% of V2, here is much smaller than the error bar. So there's just not enough data to actually confirm or disprove that you have a collectivity. There's no significance. Okay, you need more data. So what we can do in EA collisions, right? So normally you have this color dipole or this DIS scattering. You produce some final state, like jets, whatever, right? So like meson. But sometimes you can have this PA-like collisions, right? So if this gluon shell, then it can scatter with this nucleus. And so there are some cross-section fluctuation, depends on this virtual photon. You can have a small dipole or vector meson, this large dipole. If they actually formed, right, there's a certain probability, then we'll then go through hadronic scattering. You get to reveal the Fox state of this color dipole, and you can produce many particles. So this is not realistic simulation, I would say, but just proof of principle, you can produce large multiplicity. This is it. Over the full phase space, you can produce up to 100 particles by this multi-parton scattering. And then, of course, one of the advantage or obviously handle you have in DIS is that you can actually tune the X and Q square of this probe. Right? So this in PA collation, the P is fixed. There's no handle to allow you to actually change it, other than be managing. But here you actually can select. Of course, if you select a final state, it's a convolution of many different initial states, but still, nevertheless, you have some handle here.
Sorry, could you go back one slide? Which data were they? You have data?
No data. This is the MPT.
No, the previous one, the previous slide.
Oh, this is the Zeus. This is the EP collation selected. This is the Q square selection, 5 GeV, and then they select the particles. Correlating. Two particle correlation with a large rapidity separation as function of final state charge particles in this momentum range. And they try to see whether you have this V2.
Yeah. So is this analysis ongoing?
This was reported in the Quark Matter conference in the May. Yeah, so they are working on it. It's quite interesting.
Okay.
E plus minus also have this distribution, which I don't show because it also dominated by statistical fluctuations. So now you take these events, okay? You simply do two particle correlation. And indeed, you see a ridge. This is the pairs with the unit separation, indicating this is the final state effect because this is what you put in MPT. So if you select this kind of final state, you probably can actually check the nature of the particle production. What kind of particle production could have by fluctuating this dipole, okay? So is this a jet-dominated production, or this is multi-particle interaction? So let me just then show you one cute idea which I just proposed recently. You know, when we talk about the anisotropy, what we really see is that there's some initial shape fluctuation converted into the final momentum space, right? It's almost, you know, the short axis have a larger flow, long axis have less flow due to the pressure gradients. Now, if you can change the orientation of your probe, let's say you take a deuteron, if you can, you know, polarize it, you may have a possibility to either have this, you know, Jianping told me this dumbbell configuration versus this donuts configuration, which then collide with this pancake. Okay, if you do this in this case, you expect V2 should be along this direction. Okay, just like this. If you have this configuration, the flow should be along this direction. So in this case, it's orthogonal to the polarization direction. This is parallel, right? So in fact, this is in some simulation. They said, okay, take into account the mix of S and D wave component of this deuteron, and then once they can actually the wave function, they can the mix of the wave function, they can calculate what is the this polarization and this polarization, and so they can have in the central collation you can have either 11% or 5% spatial anisotropy just based on this shape colliding with this, and then you put in some hydro response which is a factor 5 smaller dilution effect, and then you put in 50% polarization. You can expect a signal between 1 and 0.5% between these two configurations. So one of the interesting things is that this is no longer two-particle correlation. You just measure single body distribution. So you don't care about the jets anymore, unless jet is have you know, I know initial state momentum correlation, which knows about this polarization direction. If that's not the case, you just measure single body distribution. You can check this idea.
Oh, but there's no prediction from CGC.
Well, this idea was proposed only 2 months ago, so you guys should.
Well, we've been thinking about that independently.
Okay. All right. Yeah, you can. The other thing is you can change others, check other species. It must be consistent, right? So the initial geometry picture and the CGC, the system size dependence is very different. So they also propose use, you know, helium-3 or other species. The wave function is very different. Polarization is different. So it will have quite different prediction than the single species.
Actually has very little TC information.
Yeah.
So I mean the picture is not quite.
Well, they already take into account this the wave function, which is 5% D wave versus 95%.
Yeah. So I don't think the picture is not that elongated.
Yeah.
I think it's, if you actually plot the different wave function,
Yeah.
it looks amazingly. Like
It's small. It's only 11% eccentricity,
yeah,
right?
I'm guessing like 5%.
Okay.
Yeah,
So let me just close saying that well, we have these multi-particle long-range correlations, right? And it's qualitatively have a similarity with between different hadronic collation system, PPP-led collations, and really it's a result of strong multi-parton dynamics in this hadronic scattering. And by going from large to small system, we are pushing the boundary between initial state correlation and final state interactions. And so the models should actually be able to cope this variation of the system. It would be useful to check this the EP and E class imbalance data because they have very different initial state. But unfortunately, right now it's statistically limited. There are some future opportunities to test this further. Let's see high multiplicity EPEA collations or polarized light ion heavy nucleus collations. To me, I already mentioned this question, right? So can final state physics shed some light on the initial state physics through the IC? I have some ideas, but I'm not going to discuss it because it's really, to me, it's very it's just a speculations so far. I would like to hear some opinions on this because I'm interested in yes, but from a different perspective. Okay, thank you.
Thank you very much.
To the idea of bridge in
Which
which
in PP, right? Okay, sure.
Yeah, so if I look at the near side of the function of delta yet, I seem to me that there is a minimum and then goes up.
Oh, this is due to normalization because we need to use a mixed event. And mixed event, the problem is you have to assume the rapidity profile you have to match. You take a minimum, but you only want to cancel out acceptance effect. So what you do is you take two different events. You calculate the pair probability distribution when the parts are not correlated to each other. You divide this same event by that. So there are some rapidity bias. So in other words, it doesn't change the smooth structure, but it raises the tail. It's artifact. Yeah. But the amplitude, here is really flat. The amount of modulation is the same. It just looks the pedestal has been raised a little.
So I recently had an interesting discussion with my MRIM colleagues. He mentioned that for your operation, you do have fluctuation by different rapidities. So in a sense, how I understand.
Well, that's very good. That's why when I say event by event fluctuation, it's not only 2D fluctuation. It's not only the fluctuation. We are really talking about spatial and momentum fluctuation in 3 dimensions beyond the DIs, because we have what we have is we have many nucleons. Each nucleons have some substructures and also have some rapidity profile coming from the stopping when you have a collision. That fluctuation is a 3-dimensional, actually 6-dimensional, but mostly 3-dimensional in the configuration space. What we see, this is interesting physics, right? When you have a stopping and you're depositing some sources, they actually could be rotated. And what we see is this leads to decorrelation. In other words, event by event, in this rapidity, it may point to this direction, go to next rapidity, point to a different direction. This is called the flow decorrelation. This has been observed in the lead, but also in P-lead collisions. PP, people haven't done it, it's difficult. But there's a, so to me, what is really interesting is that you have this multi-parton system, a bag of partons, right? Boosted. You collide these 2 bags. What determines where you deposit these energies in rapidity, right? I mean, it's highly non-trivial, but then once you deposit them, they actually can have a different orientation.
So then I have difficult to understand your long range because
that decorrelation is small effect. This is 20%. Okay, it's not. It's
so
not.
It's on top of that. You have
Yes.
10%.
Yes.
Can you also sorry, you have to jump back. So maybe just ask this question. So what do you learn if you have, for example, ESC measures we need simulation of non-zero V2 or long-range correlation? What do you learn if you compare that with PA, for example?
Can I add also to the question, because I had some similar. What do you have to look into, right, to see this?
To see what?
It's like long range current.
Oh, I see.
So it's it's even the more basic.
I know.
So
I give my example, but this is a specific configuration where you have this hadronic, let's say, QQ bar fluctuating into vector meson, but then collide hadronically with the nucleus, right? This will give you, but this is no different from fundamentally from PA collision, other than you have different initial conditions. What I think is interesting is the following. You're talking about energy loss. It's a final state, right? Whenever you have a final state rescheduling, you could produce multi-particle correlation, but this may be small effect. So in other words, for me, the DIS already gave me the initial state, which I think must know that also the momentum correlation and putting the CGC effect is pretty good for me, but also the theory need to work on it. But what I'm more interested, I think, is beyond this is that since you can access much more complicated initial state than DIS in the PP condition, much more complicated final state. What we can do by marrying this final state and its correlation and event by event fluctuation, from that, together with modeling, we can learn something new in the initial state. Okay, CGC is one of model people using to try to learn this. So I want to go to, in principle, the other way to, but I don't know, I don't have, maybe this is not what you're asking for, but.
Well, I'm more asking what was there, although I don't think you answered. Maybe it's a famous question, but not mine. And what are you going to measure? It's kind of a simple question.
Oh, I already give you, so in this, I will select the event with large multiplicity, let's say plotted as function of charged particles, up to, let's say, 100 particles. Then I get to do multi-particle correlations, separately rapidity, for example, and fully decompose it. Okay? I mean, if I see V2, V3, I know it's long-range continuous correlation. I could ask, is this different from what we see in PP collection?
The problem is you have a very complicated interpretation, like what you have for PP. I mean, for example, back 10 years ago, 5 years ago, if I talk to Roger, he would definitely say, oh, PP, if it's in long-range range, must come from CGC. But now you have very complicated interpretation of it. So I'm worried if even you do the EA in the future, there may be also kind of very complicated.
It is. But still, I think the question remains is that whether it's could come from initial state or final state. If the final state is weak enough, because you may not produce
100 particles.
Right. You certainly produce less particle, but the question is, it will have different rapidity structure because the probe is different. The question will be, what you can use to produce this momentum anisotropy. All right. Let's see can you do it from the purely initial state? Or you have to imply, if there's really no final state in action, and you have some mechanism to produce in this.
I don't know. I mean, maybe in the future even, say you also maybe have leader bound there. I mean, nobody knows.
Could be. As I said,
for example, why people still looking at E plus E minus, that's kind of surprised me and also shocked me. And then they found another way too.
No, they didn't find anything. Plus minus.
Who told me? I mean, some rumors say that.
No. So what, as I said, they will measure a signal.
No, some series.
Oh, I see. Theory. Okay, they just you produce more than multi-part on final state. You have to have only through fluctuations you can do that, right?
Wait, there's a series who
working on the E plus minus data,
but using analyzing the data.
Yeah.
No, not from data. Data have no indication.
I think they are looking back E plus. Maybe I heard different.
No, I think this is really, you need to be really careful. You can get a large V2 just from digest. You have to really suppress that.
If they are talking about digest, that's too naive, right? I think they are really trying to look for.
But at very high energies, even in plus and minus, you have this nice picture with dipoles for TIS and saying that dipole nuclear scattering is like PA in some ways. And that might be true. But for E plus and minus, you can think of it as dipole scattering at very high energies.
Probability is small,
photon which fluctuates into a QQ part pair, and then you have all those. Yes, and of course, if you have it's a suppressed. The rate is small because you need 2 powers. Actually, 4 powers of alpha and m, right? So
you say there's a series already predictable.
So actually, there's one thing that I'm interested in, I can tell you, which is you can have a multi-particle production. Basically, just multi-particle interaction, but quite a low multiplicity. Because multiplicity you can select. You can read on the jets, make sure this event does not have jet. The question will be, are those partons are coded in the long range? I mean, we see the V2 in the PP collision down to, let's see, 20, 30 particles, right? I think this event maybe to me is quite interesting is if you have a multi-particle correlations, right?
I strongly suggest you stay in maybe another 2 weeks. I think all and Edmond, I think they will talk about this. Europe will talk about this as well.
Yeah, so week 6 we'll have discussion.
I mean, in particular, for example, I know recently Al and the other people are looking for this fluctuation contribution to DIS and diffractive DIS. I mean, this could lead to the multi-particle
That
correlation.
doesn't give us this talk yet.
I mean, you should ask him to talk about it.
So I think that my question I want to cover is this question have been thinking not for so long, but for I listen to talks. I've been thinking about this. I mean, what you might have talking about, right? The jet quenching must be consistent between hot QCD and cold QCD. I think there, jet substructure, all those are really, really good one way to do it. But the question I want to go the other way is really, because we all talking about QCD, but the different is we starting from a different initial configuration. They must be related, but I just don't know. Maybe this is already it's not leading order question we're asking, right? So, but I actually quite interested in knowing some good ideas along this direction.
I just have small comment, so I think you guys should think about it. I mean, this part was not discussed extensively last EIC white paper. I mean, Raju wrote a little bit on this, right?
On the ridge.
On the ridge, but it's to maybe more dedicated level, or maybe I don't know. I mean,
No, it's a good point. It will be discussed in week 6. I mean, I don't want to say anything.
I think
very strongly because there are some calculations, but I think the existing calculations don't quite address looking for long-range correlations in EP or EA relations. So all the calculations are more about nucleus or very fluffy proton nucleus relations.
It's also a way to attract young people to participate, right? If maybe some good idea can come about.
Right.
All right.
Okay.
So maybe it's good to stop here. So let's thank John again. Coffee break and